Gaussian elimination. What this is like the elimination technique you use for systems of equations, but with matrices. Here is a really easy systems of equations to solve. I hope you can see that y is equal to 2. And once you realize y is equal to 2, it would be really easy to substitute back into the original equation. Put the 2 in for y, and you would get your solution as -1, 2. Now, the matrix that goes with this one, and here is a new definition, an augmented matrix. So with an augmented matrix, we basically make the matrix, but we add a straight line where the equal signs were. So it's really, hopefully you can see it is exactly the same thing as this. And life is super nice if there's a 0 in the bottom corner, because then you would know what y is. Or you would at least have an equation that would be really easy to solve for y, and then you could work backwards and solve for x. Now, having it in this form, where all the zeros in the bottom left corner, or all the elements in the bottom left corner are zeros, is called row echelon form. That's on your calculator as graph. We're also going to learn about reduced row echelon form a little bit later, as opposed to just rep. Okay. And so what we do is we do the same idea that we do for elimination, where you're getting rid of one of the variables, and this is called Gaussian elimination. And it looks like this, okay? You create your augmented matrix. You can draw a straight line in here, where matrix A is all the coefficients, matrix B is the answers, and then we call a bunch of row operations, things you can do from one equation to the other equation, to eventually get that 0 in the bottom left-hand corner. And it's the same idea if you had something like this. Okay? If I had x plus 3y equals 5, and 5x minus 2y equals 4, can you see that if you had this equation and you wanted to use the elimination technique, you would probably take equation 1 and multiply it by -5, and then add it to equation 2. And you would get a 0, and you would get a new equation. Now, would this be different if I move the equation to the top? Am I solving something different? No. So one of the things you can do is you can interchange any 2 rows. You can move your rows around. It's still the same equations, whether you had this one on top or this one on the bottom, right? You can even decide, oh, I want to make y first and x second, or x first and then y second. The only thing that you have to make sure is you remember all of these things that you did, because afterwards you're going to be like, okay, I solved for x or did I solve for y? So generally, we generally like to keep x first and y second, just for our own mental sake that we're not overthinking things. You can multiply any row by a non-zero number. That's just like we did in here. I multiply by -5. If I multiply everything in that row by -5, it doesn't change its value. And then you can add or subtract any row to another row. And then once you get those zeros in the bottom corner, you just have to work backwards to find all of your answers. So this is what it's going to look like and how we're going to show our work for this. So we start by making the augmented matrix. 1, -2, 1, and 4. Those are our coefficients, 10 and 16. We're going to remind ourselves our goal that you're making this spot right here a 0. And the way that we're going to show these row operations, we're going to draw an arrow saying, I'm going to change something. We are going to say what we're going to change. I'm going to change row 2, and just deciding I'm going to make the 2 big. I was thinking about making the 2 small. It really doesn't matter. Do you want to make a little 2 beside it, or do you like a big 2? That's fine. Okay. We're going to take row 2, and we're going to change it by doing row 1. Oh, I think I like small numbers. It just naturally happened there. Okay. Minus row 2. Yeah, it's going to. I like it. Sorry, guys. Making this small now. Oh, yeah, that looks good. So I'm going to take row 2, and I'm going to change it. And how am I going to change it? Well, I'm allowed to do anything I want. Multiply rows, add rows, subtract rows, interchange rows. So I'm just going to take row 2 and subtract row 1. Well, what does that mean? I'm only changing row 2. That's why I wrote row 2 first. So that means I can rewrite row 1. Row 1 hasn't changed. But row 2, I'm now going to write row 1 minus row 2. So that would be 1 minus 1, which gives me the 0 that I wanted. It would be negative 2 minus 4, which would give me negative 6. And it would be 10 minus 16, give me negative 6. What was our goal? To get that to 0. We've done that. So now we can like, well, what does this mean? Well, this means that negative 6y equals negative 6. Is that easy to solve for y? Absolutely. Y is equal to 1. Then, you could substitute in x minus 2 times 1 equals 10. And write our solution as a point. And our solution is 12, 1. You can always go back to your original equation here and double check. Does it work? If I plug it into both equations, does 12 and 1 give me the actual solution? It does. Things are good. Here's our solution. This is Gaussian elimination. Okay? You might still argue, I still like regular substitution and elimination for a 2 by 2. But maybe when we get to our 3 by 3s, we're going to like this even better. Okay? 1, you're not writing all the variables every single time. So you're making your life a little bit simpler because you've got an organization technique to keep things organized, but you can do lots of manipulations at a time. So again, I'm going to want to change row 2. We'll do dots, so you can use it. Like, there's not really much official, formal ways of writing. Some people use an equal sign there. If you like that better, go for it. I just did dots. I'm going to change row 2. I'm going to change row 2 by taking row 2, I want this to be a 0. Can you see that if I took this and subtracted 2 of this one, I would get 0? So I can write that. I'm going to take row 2, and I'm going to subtract 2 row 1s. Well, I think that's why I like the little number. That means row 1 isn't changing. Okay? Now I want you to take row 2 and subtract 2 row 1s and write the next line. Because this is where the mental math is. None of the mental math is hard, but the mental math is super easy to make mistakes. So if you took row 2 and subtracted 2 row 1s, I will give you the first one that's easy. That's a 0. Can you figure out the other ones? Did you get, are you ready? Or yes? Did you get 7 and 28? No. Oh. Okay, so here I have row 2. Minus 2 times 3 is going to be plus 6. And here I have 24. Minus 2 times 2. Minus 2 times negative 2 will be plus 4, 28. This unit is going to be your favorite. And once you get that 0, that tells you 7y is 28. So y is 4. Then, presents for me?
Graph paper.
Yes.
Can you use it?
Obviously.
Great, because I have no need for that. All yours.
Perfect. Hey, we are going to do a graphing activity. Then, as a result, you can plug in either equation. Just use the first one. Add 12 to both sides. Always write your x first, because it's a coordinate of where these two lines intersect. A couple of things to notice, okay? If you were solving this one with elimination, I'm thinking you probably would have multiplied the second equation by 3 and canceled out the y's because you would have thought that was easy. Okay, perfect. That's great for elimination. Interestingly though, with this technique, it wasn't very hard to get that 0 anyways, even with the x's, even though we might theoretically look at this and say the y's would have been easier to get. And then the question is, well, if it doesn't matter, why does it need to be this lower left-hand corner to be the 0? Why couldn't I have this corner be 0? Well, we'll see that, especially when we get to the bigger ones that are 3 by 3.
The solution is supposed to be 5, 4.
5, 4. Thank you. Look, I saw this number here, and I wrote it down. There we go. Yeah. So I wrote -2 probably right after I said be very careful that you write the x coordinate first. And then I didn't think at all about the y coordinate being correct. What do you do if things aren't in the augmented matrix form? Well, first of all, you're going to have to rearrange things. So I would take this one and I would write -3x plus y equals -2 and x plus y equals -6. So see if you can figure out how you can make that bottom corner 0. Top row is not going to change. Makes sense that you could take 3 row 2's and add it to row 1.
But is it wrong if we say R2 plus 1/3 of R2?
No, it's not wrong. The only thing with 1/3 is your chances of making a mental math mistake using 1/3. I was going to say increase, but they're the same. You make the same mental math either way. It's the same odds of making a mistake, because we make a mistake every single time, so it doesn't increase or decrease. But no, can you see that this, though, would be easier, hopefully, because you're not dealing with the fractions. So the question was, could I use 1/3 and then add it? Yes. But that's harder mental math. It's easier to times this one by 3 and add this one to get 0. Times this one by 3 gives me 3 plus 1, 4. Negative 18 plus negative 2, negative 20. Look at this strategy this time so I don't screw up. I circled the y. It's going to help me realize what y is later. And now I can go to any equation. Negative 5 equals 3x minus 2. Negative 3 equals 2x. X equals negative 1. Circle that. And my solution. Well, I like that circling idea. Since circling, I have never ever made a mistake. Oh, that would have been dangerous if I had made a mistake. But I think we're good. Again, if you were using regular elimination, you would have eliminated the y's. In fact, some people in regular elimination, I'll do it here in red, would have just said, oh, let's just subtract right away. Y minus y is 0. 3x minus a negative x, 4x, negative 2 minus 6, plus 4. And it would not be hard to get x is negative 1 with regular elimination. Perfect. Okay? And really, with a 2x2 system, this elimination technique or the inverse technique that we learned probably aren't better than the first techniques of substitution and elimination. But as we got to bigger equations, like solving the 3x3 with elimination, it started to get, your data started to get all over the place and more complicated. So we're going to find that this is going to be nice once we get to bigger ones. Yeah, so let's skip this one. We've done. Do you guys get the idea? Okay. Let's just make, we're going to make one with a 3x3. Right? So we're going to, let's put an X through this one. We're going to create a new equation. I'm going to make it nice and easy. X plus 2y plus z, that's going to equal 8. And 2x minus y plus 2z, that's going to equal 6. And x minus y minus z is going to equal 0. our big matrix here is 1, 2, 1, 8, 2, negative 1, 2, 6, and 1, negative 1, negative 1, 0. That's our goal. All three of those have to be zeros. Okay? Now, when you did a 2 by 2, it's really, we've developed a technique with a 2 by 2 to get the 1, 0. I think you're pretty good at it. Okay? When we have a 3 by 3, and I'm going to color code this, we are going to find these two first, and then that one second. And it will always be this way, because if I make these two zeros, what you have down here in the bottom right is a 2 by 2 that you have to solve. And if you think about elimination, when we did this with elimination, we chose one variable to get rid of. Okay? The difference with Gaussian elimination is you are choosing the x variable to get rid of. That's what the purple is saying. You're getting rid of two x's. You're making them zeros. Then, that gives you a 2 by 2 with y and z, and then you eliminate the y to get z all by itself. Well, I'll color code it really nice. So the first thing we want to do is get both of those zeros. And in row operation forms, okay, one of the rows I want to make a 0 is row 2. Can you see that if you took row 2 and minus 2 row 1, this would be a 0? So if I took row 2 and subtracted 2 row 1s, that would make this a 0. And at the same time, I can change row 3. Can you see that if I wanted to make this a 0, I could take row 3 and minus row 1. I first look and decide, well, which row am I not changing? I'm not changing row 1. So I'm going to keep this as 1, 2, 1, and 8. Okay? Test your mental math skills. Can you take row 2 and change it by doing row 2 minus 2 row 1s? And then can you take row 3 and change it by doing row 3 minus row 1? And in this unit, you are not allowed to make mental math mistakes. Your happiness depends on it. I'll give you hints. These are both zeros. Make sense? Yes. just nervous. Are we ready? You got the rows? Okay. Think so? Just vote? Got one?
Yeah.
Okay. So let's see what ended up happening. So if I took row 2 and I minus 2 row 1s, did you get a -5 then? So here's row 2. Subtract 2 times 2. Subtract 4. -1 minus 4. -5. Row 2. 2 minus 2 row 1s. 2 minus 2. You get 0. And here, 6. 6 minus 16. -10. Good? And then finally, row 3. Row 3 is just minus row 1, that's 0. -1 minus 2, -3. -1 minus 1. Oh, you're right. Just bugging you. Oh, sorry. I shouldn't have done that. Yes, -1 minus 1, -2. And then 0 minus 8, -8. Now, we've already solved for x, but in the Gaussian elimination, we make this one 0. We've already solved for y. -5, y equals -10. I hope you can see that y is equal to -2. And if you were doing substitution, y is equal to +2.
Yeah, I was just saying, yeah.
And if you were just doing substitution elimination, you could go from here and you would be done. Okay? But in Gaussian elimination, now we want to make this one a 0. That'll be our next arrow. We need to change row 3. And you have to only use row 2. The reason that you're not allowed to use row 1 is because then you will not have a 0 there anymore. So if I'm going to multiply and add and subtract rows, I now have to use row 2 and row 3 to make this a 0. And this is a little bit more complicated because I have a 3 and a 5. What am I going to do? I'm going to take, right, it's like getting a common denominator for a fraction. With 3 and 5, it would be 15. So I'm going to take 5 row 3s. That would give me -15. And then I'm going to subtract 3 row 2s. Because this would be -15 plus 15 would give me 0. Does this make sense? For this step here, we have to use row 2 and row 3 in order to preserve those zeros. If you introduced row 1 and added it to that equation, now there would be a number back in that 0 and you'd be like, oh, I got to go back to where I started from. What's really happening here is we are in this orange step. Now we have reduced our solution to a smaller 2 by 2 matrix by putting those zeros there. And so now we're trying to solve that 2 by 2 system. You're not going to use row 1 for that. You are now only going to use these new 2 rows. I look at my arrow. In my arrow, I say I'm changing row 3, so that means I'm going to rewrite row 1. write row 2. And now what is my row 3? Well, because row 3 and row 2 are getting added, 0 plus 0, that would still be 0. We've done things, so I have negative 15 plus 15, that makes this 0. And 5 times row 3 will be negative 10 minus 0, this will be negative 10. Negative 40 plus 30 makes that 7. Okay? Again, with positives and negatives, you got to be really careful with your mental math. So, can you see that negative 10z is equal to 7? And that z is going to equal negative 7. Did I make a mistake?
Would it be negative 10 instead of 70? Because you're negative.
Oh, yeah. Man. Tell you. Because what do we got here? We've got negative 40 plus 30. Negative 10. Luckily, we can just make that simple manipulation and change those into ones.
And that would be positive.
What?
Because it's negative.
The answer is,
There we go.
oh, yes.
There we go. And once you've got Z, and we usually, once you get Z, you'd have to plug it in to the second equation, because there would be a Z in there. This one, we're lucky there's another 0. That made solving for Y easier. But now that we have Z and we have Y, we can go to our first equation, which says X plus 2 times Y plus 1 times Z is equal to 8. And you get X is equal to 3. And your solution, X first, then Y, then Z. Is our solution. So the mathematician Gauss, who developed this, that's why it's named Gaussian elimination. Another mathematician comes along and says, I think we can do a little bit more. Why don't we also make zeros up here and change it completely to the identity matrix so that there's ones on the diagonals? That mathematician's last name was Jordan. And we get Gaussian-Jordan elimination. Okay? Now, color code. We want ones here, zeros here, zeros here, and numbers here. Color coding, we are still going to do this first, then this second. I'm going to run out of colors. You ready for the 1, 2, 3, 4, 5, 6 things in order that we're going to do? remember the 6 things in order is if you think about them, it's the only order that makes sense. But we haven't thought about it yet, so we're going to learn. Now, did it make sense that we could get those, like when we did the last example, it made sense that we could get the purple zeros first. And then I think it makes sense that you could get the orange 0 next. Okay? What Gaussian Jordan would look at the equation that we just did and say, you know what you should do next? You should just take row 3 and divide it by -10, because then you would get a 1 there. That would be super easy to get a 1 here. By just taking row 3 and dividing it by -10, and then you would get a 1. So that will be the third thing that we're going to do. So we're going to get zeros, then we're going to get another 0, then we can easily take that row and divide it to make that a 1. And now we sort of reverse the process up. So if I found those 2 zeros first, now working backwards, I will get those ones to be zeros. That will be 4. Then once you have everything, yellow is a wonderful color. That will be 5th. I need more colors. Then we can make that one a 0, 6. And finally, you want pink. That will be 7th. The 7th step, reduce row echelon form. It's much easier with a 2 by 2 to get it into reduced row echelon form. Oh, look at that. Oh, such good colors. And they're all pastels. Oh, see? Who knew math class could be so much fun? This is the math class fail. Just red, blue, and black.
I am boy, not girl.
You
I am boy, 7 colors, different colors.
You know,
We need to make sure that we.
that's all you need.
Yes.
But I have the
You gotta redefine your gender roles.
I know.
Okay. So with the 2 by 2, first thing we're going to do is we want to make this one in row 2 equal to a 0. Pretty easy. Would it matter if I do row 2 minus row 1 or row 1 minus row 2? No. You can, the order doesn't matter. Whatever you decide to do to equations. So row 2 minus row 1. Perfect. That means row 1's not changing. 1, -2, and 10. And I get my 0 here. 4 minus -2, 6. 16 minus 10, 6. And we just keep doing arrows. So now I can take row 2 and I can change it by dividing by 6. Because I want that to be a 1. Row 1 didn't change. 1, -2, 10. 0, 1, and 1 now when I divide by 6. Now I want to change row 1 because I'm hoping to get this to be a 0. I can do that by taking two row 2s and adding it to row 1. Now I'm not changing my row 2 this time, so those stay. And 2 row 2s, that's still 0 plus 1 would still be a 1 there. 2 row 2s plus this will be 0. 2 of these plus this will be 12. Sometimes you still have to divide row 1 to get that 1. This time we got a 1 already. This is reduced row echelon form. Right? What's really nice about this? Y is equal to 1. X is equal to 12. You see the answers directly. Okay? And our solution is 12, 1. And this is the same one that we did earlier. I know, the space is terrible. You almost, I think, I have loose leaf. You might need loose leaf for some of these, because the amount of space is huge. Or would you like to use graph paper? Your choice. Loose leaf or graph paper. I will take out both. This is really a social experiment on peer pressure. Which one? This one?
No, graph paper.
Oh,
I think it's 2.
yes.
Oh, good. My social experiment is working. And someone's going to come to school on Tuesday and say, I couldn't do the notes because I didn't have graph paper.